Yeah, so good morning, class. Let us begin today's digital electronics class. So, before moving to next topic, let us revise. Uh, in our book, that is the Morris Mano, is author, and title of the book is Digital Design. So, in that, first topic is the signed binary numbers. So, signed binary numbers means we are concerned how to represent negative numbers, negative binary numbers. So we come to know that there are three ways through which we can represent negative binary number. So first method is known as, let me change the color. Okay, first method is sign magnitude representation, which is given here. It says that when MSB side or leftmost bit is 1, it indicates this is the negative number. And then just here 4-bit, for example, this represents your magnitude. Second types of representing binary negative number is signed one's complement representation. So this is the second method, in which it says that we keep this leftmost bit as 1. Beside that, whatever number is there here, this magnitude portion, this magnitude is represented as one's complement form. Okay, so the number which have here, suppose 1 0 0, this is the magnitude. Its one's complement will be 0 1 1 0, and this is what is written here, 0 1 1 0. Okay, and rest indicates this is a negative number. So the second method of representing negative binary number is signed one's complement method. Third one is signed two's complement method of representing negative binary number. What does it say? It says that MSB or leftmost bits are 1, just to indicate this number is negative. But this magnitude, which is here, actual number is 1001. We take 2's complement of this to represent into sign 2's complement method. How can we take the 2's complement of 1001? The simple method is that take 1's complement and then add 1. So we have taken already here 1's complement, this 1001 complement, 1's complement of this 1001 is 0110, and then to take 2's complement, we just add into 1's complement. So 0 plus 1 will be 1. 1 is here, 1 is here, and this is 0. So this is the 2's complement form of representing 1001. And you see the same number is written here, that is the magnitude. So 0 1 1 1. So this is the three way of representing negative binary number, which is given in here table form. Okay, so here magnitude is represented by 3 bits. Okay, 3 bits. So if we represent binary number using 3 bit, so it will go from 000 to 111. Number wise, it is 0 to 7 in digital in decimal form. Okay, so that is why number is given here. Now, since we are covering positive as well as negative numbers, so to have a complete table, all forms are given. And what we are observing through this table, we are observing that as far as positive number representation is concerned, in all three methods, whether it is sign magnitude, whether it is sign one's complement method, or sign two's complement method, representation of positive binary number are same in all three formats. Okay, you just check, you just observe it. The difference comes when we want to represent negative numbers. Okay, I will remove this one, earlier one, so that you should not get confused. Let me stop the video to save the bandwidth. Now erase it. Okay. You see negative numbers, particularly from -1 to -8. You see here, if you want to represent these negative numbers, so in sign magnitude, sign 1's complement, sign 2's complement, their representation differs based on the definition. Okay, this we have covered last time. Now coming to about arithmetic addition. Arithmetic addition in sign numbers. So let us read two important points here, which we already know. Only it is a matter of revising it, recalling it. This is the two important lines. So let us read it. What is this? The addition of two numbers in the sign magnitude system. The sign magnitude system follows the rule of ordinary arithmetic. Means whatever we were doing earlier, whatever rules we know in ordinary mathematics as far as addition is concerned, same is applicable for sign magnitude system also. What is that? It is if the signs are same, like -2 plus -2, okay, or 2 plus, both have same side, this is plus and this is also plus. Okay, so what does it say? If the signs are same, that is here negative, negative, positive, positive, same, we add the two magnitudes and give the sum the common sign. So we add magnitude portion. So 2 and 2 will be 4, and put the common sign. What is this common sign in this? Negative. Similarly here we add the magnitude 2 and 2, it becomes 4, and the common sign these two numbers are plus. This we already know. This is what is telling that addition of two numbers in sign magnitude system follows the rules of ordinary arithmetic. This is one thing. Second case, if the signs are different, means suppose this is 2, we want to add +2, okay, or 2 plus -2. Both cases may be there. I am taking simple example. We subtract the smaller magnitude from the larger. Okay, let us take something different number, 3. Okay, if the signs are different the way here, we subtract the smaller magnitude from the larger and give the difference the sign of the larger magnitude. What does it mean? It means that if while doing addition, we see these two numbers have different sign. It 2 has minus sign and 3 has plus. So what do we do? While adding, we subtract the smaller magnitude. So what is the operation which we do first before addition? That is the comparison. We have to compare these 2 and 3 and decide which one is the smaller. That is the 2. So 2 should be subtracted from the 3. So we subtract 2 from 3, it will be 1, and then put the sign of larger magnitude. So larger magnitude has which sign? Larger magnitude is 3, and 3 has the plus sign. So we just put plus. Same goes here. If we compare these two magnitudes, so 3 is uh, 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 no, 2 is 2 plus -3. What will happen here? Magnitude wise is uh, 2 is smaller than 3. Yeah, 2 will be subtracted from 3, so it will be 1, and put the sign of larger magnitude. What is the sign of larger magnitude? That is minus. Okay. So this is what is written here. If the signs are different, we subtract a smaller magnitude. In both cases, 2 from the larger is 3, and give the difference. Give the difference means this is the result. Give the difference the larger magnitude. Okay. Give the sign. Give the difference the sign. For example, is this plus 25 plus minus 37 is equal to what? We we put the sign of larger magnitude, this minus outside, and subtract the smaller quantity from the larger quantity. This we know. I'm just trying to elaborate. It's done by the subtracting the smaller magnitude. Is this okay? So nothing is very special here. We already know these things. So same thing it is followed in sign magnitude system also. Only thing is that we have to deal with the binary numbers. Okay, but think about what is the issue here. Whenever we are going to implement with the help of computer, there is a issue. What are the processes involved in that? So there are two processes involved in that. Let us see what is that. This is a process that requires a comparison. You have just seen here comparison of the sign and magnitude. First, even before doing this your addition, we have to compare which one is smaller, which one is the larger. It means we need a comparator circuit, and then perform either addition or subtraction. So two-step process. This ordinary mathematics is a two-step process while doing the addition. The same procedure applied to binary numbers in sign magnitude representation. In contrast, the rule for adding numbers in sign complement does not require a comparison or subtraction. See, here things comes into your picture. If for binary sign complement, if we do adding, then it doesn't require a comparison and subtraction. Then what is required? It requires only addition. So this is the biggest advantage if we are dealing with this signed complement method. And the procedure is very simple and can be stated as follows for binary numbers. The addition of two signed binary numbers with negative numbers represented in sign 2's complement form is obtained from the addition of uh, two numbers including their sign bits. A carry out of the sign bit is discarded. This is the rule. What does it say? It says basically this operation, third one, uh, this number. Okay, this one. So in ordinary mathematics, comparison. After comparison, what do you get? You get greater than is equal to less than, and after that you have to do either plus or minus. These are the two-level process in ordinary mathematics. But if we deal with sine 2's complement system, it's if we express sine even positive number is sine 2's complement, it doesn't have any effect. Positive numbers are same. You see, positive numbers are same in all as far as sine 2's complement method is concerned. But negative numbers, we are talking about now negative numbers. Whenever we are doing the operation of addition, or even subtraction, the addition of two signed binary numbers with negative numbers represented in sign 2's complement form is obtained from the addition of two numbers, including the sign bits. Okay. Here example is given. This is the bigger example. I will take smaller example. Suppose here I take 2 and 3. Okay, so that you will easily recall. So how can we? So these two numbers are plus. So in 2's form, let us write these numbers into sign 2's complement form. Okay, so plus 2. How can we write plus 2? So 0
0 1 0.
indicates 0 indicates leftmost 0 indicates that is this is a positive number, and after that 0
1 0.
no 0 1 0. Okay, three what is called, we are using 3-bit. Okay, just so that you can verify from this table also. So you see here plus two is here, and this is your number. Okay, 0010. Is it the same what I have written? Yeah, 0010. ठीक है? Okay, बोलो भाई.
Yes, sir.
So now next is 3. How can we write 3? 0. This is the MSB, which indicates this is the positive number. And after that, this is the 3. How can we write 3? 0, 1,
1, 1.
1. And now add. Whatever operation is doing here, I am doing with small number so that you can understand easily, and then you can follow this one also, no problem. And do the addition operation. So 0 plus 1 will be what? 1. 1 plus 1 will be 2.
0.
1 plus 1 is equal to 2 now. And how we write 2 to binary number? Like this. So at unit place, it will be 0 and carry will be 1. Is it okay?
Yes, sir.
And then 1 plus 0 will be 1. 0 plus 0 will be 0. So 0 indicates here this is a plus. And what is this number? Anyone? Bolo bhai.
5.
Very good. So this is your 5. So 2 plus 3 is equal to 5. Okay. Now let us take this one. So it says that we have to write -2 and you have to write 3. So how can we write -2? In 2's complement
1,
form.
0, 1, 0.
This is what? Let us write first magnitude. Magnitude is written like this: 0, 1, 0. This is what we have written here. Okay. And takes 1's complement. How can we take 1's complement? This will be 1, 0, 1. And then add 1 to take its 2's complement. So 1 plus 1 will be 0, carry 1, and this is 1. So -2 is 1, 1, 1, 0. Is it okay? Okay. So 1, 1, 1, 0. Can we check? No. 3 है ना? हाँ ठीक तो है. 1, 1, 0. -2 is here. I will take now red color. -2 is here. ठीक है? बच्चों 1, 1, 1, 0. So -2 and +3. +3 will be as it is. That is the 0, 0, 1, 1. Then add. So 0 plus 1 will be 1. 1 plus 1 will be 0, carry 1. Then 1 plus 1 will be 1, 0. And this will be 0 here, carry 1. 1 plus 1 will be 0. And carry will be discarded. This is what is written here, rule. A carry out of the sign bit position is discarded. Okay, so we are not writing. So this is what? Okay, this is why answer is not correct. +7. +7 will be. Arey bhai.
So it will be
-2.
+1, sir. -2 plus 3 will be +1.
Her answer सही तो है. Sorry, why I was confused with this. Okay, so this zero indicates what? This zero indicates this is a positive number, and 0, 0, 1 is what? 0, 0, 1 is 1. So answer is okay now. ठीक है, convincing. बोलते जाओ भाई. You just say yes or no so that I can proceed. Now let us do this
Yes, sir.
exercise. Let us do this exercise. This is what? This is 2 and this is -3. Okay. So how can we write 2? 0, 0, 1, 0. How can we write -3? So see, this is +3. So +3 is 0, 0, 1, 1. This will be minus, so MSB will be 1, and take the 2's complement of 0, 1, 1. How can we take 2's complement? This will be 1, 0, 0, and then add 1. It will be 1, 0, 1. So 1, 0, 1. So we can write minus 3 as 1, 1, 0, 1. Okay. After that we add. So let us add. So 0 plus 1 will be 1. 1 plus 0 will be 1. 0 plus 1 will be 1. And 0 plus 1 will be 1. Okay. So now you see this one indicates what? This one indicates negative number. And these three, 1, 1, 1. 1, 1, 1 is nothing but 1, 1, 1 is nothing but uh,
Minus
2
1 inside 2's complement.
minus 1 in 2's complement form. But this 1, 1, 1 may not be intuitive to us. So let us take its 2's complement, then we will come to know. So this is 0, 0, 0. It becomes 1's complement. And then add 1. So it is 1, 0, 0. It means this is what? This is 1. Okay. So this 1, 1, 1 is nothing but 2's complement of 1. Okay. So answer is 1. So overall answer become minus 1. So minus 1 can be written as 1, 1, 1, 1. Let us check in table. Look here. Okay? Minus 1 is written as 1, 1, 1, 1. Okay? So this is minus 1. So this exercise we have done here. And now last one. Last one is minus 2 minus 3. So minus 2 can be written as like this 1, 1, 1, 0. And minus 3 can be written from here 1, 1, 0, 1, 1, 1, 0, 1. And add it. So 0 plus 1 will be 1. 1 plus 0 will be 1. 1 plus 1 will be here 0. Carry 1. And then 1 plus 1 plus 1 will be 3. This 3 means 1, 1. So 1 we are writing here. And another one is coming as a carry, and carry has to be discarded. So now this is the answer. This answer means your MSP or leftmost bit is 1. It means the answer is in the negative. And this is the 2's complement forms of which number? 0, 1, 1. Let us find out what it is 0, 1, 1. 0, 1, 1. Take the 2's complement, we will get its magnitude. So 1's complement will be 1, 0, 0. And then add 1. So it will be 1, 0, 1. So 1, 0, 1 is here. And what is this 1, 0, 1? Magnitude? This is 5.
5.
So we can write here minus 5. And this is, we know from our general knowledge that minus 2 plus minus 3 will be minus 5. Okay? So you got it? So what is the beauty of this dealing with the binary number? Beauty of the dealing with binary number and that 2's complement form is that we need not to compare and then subtraction. We only add it when the number when signs are different here. In ordinary mathematics, what we do? We compare, and whichever number is less, we subtract that number from the larger and then put the sign of larger number. This is what we do in normal mathematics. But when we are representing this number into binary, 2's complement form, we don't bother about all this comparison as well as subtraction. We simply do the addition. Okay, so this is how we simplify the hardware implementation into computer. Okay, so note that negative number must be initially in 2's complement form, and that is if the sum obtained after this. Please read all those things. Okay, I have given in nutshell. And the subtraction of two signed binary numbers when negative numbers are in 2's complement form is simple and can be stated as follows. This is the method we have to understand. Take the 2's complement of subtrahend, means the number which is going to be subtracted. Subtrahend including the sign bits. and add it to the minute, means from where you are going to subtract, including the sign bit. A carry out of the sign bit is discarded. Okay, so even in subtraction, what we are going to do? We are going to do add only. So when we are adding that, and that case also we are doing the addition operation, and when we are doing subtraction, at that time also we are doing addition. See, this is what is something new we are learning here. Only issue is that we have to take the 2's complement of subtrahend and then add. And why you will convince that this procedure is okay? The procedure is like this. Here you see, suppose A is represented whatever plus minus, then minus sign is there, which is our task, that is the subtraction, and this number, suppose this is a plus, and in another case this is a minus. So if it is a plus, it can be represented this way. If we just interchange the sign of this B with this operator, okay, and that is quite sensible. So plus is coming out and this minus is coming inside this, and then this is very easy to represent minus number into complemented form. So here this is how we do. So we do only addition operation, although it was asked to do the subtraction. Similarly here, A is plus minus, that is the minute, and this is the B is the subtrahend. So we take the 2's complement, okay, so that we can express here as minus B as a plus B, and this plus operation is it is going to. Here ordinary mathematics says that plus minus A minus of minus B is equal to plus minus A plus and this plus B. I think this equation we are very familiar. Only we have to do now with the help of sine 2's complement. So this procedure is adopted because a subtraction operation can be changed to an addition operation if the sign of the subtrahend is changed, and is demonstrated by the following relationship. So we can take the example and we can perform, okay, these operations. Clear? Class, any question? If you have any question, please let me know. Otherwise, we can move further. Okay, now coming on the binary codes. So binary code. So this is BCD key code. Okay. We know this binary number whose base is 2. Radix or base is equal to 2 in binary number. So this is a number, but what we are talking about here now, code. There is of course relationship, but these numbers follow some weight mechanism. What is that weight mechanism? I will write here. Suppose 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, and so on. So this is your base, and then some value and where n is equal to 0, 1, 2, 3, 4. Okay, so let us evaluate as far as binary number is concerned. Let us evaluate its weight itself. 2 to power 0 means 2 to power 0 means 1. बोलो भाई. 2 to power 0 means 1. 2 to power 1 means 2. 2 to power 2 means 4. 2 to power 3 means 8. Okay. Most of the time we deal with this by 4 bits, so that is why I'm going to 4. We can extend this left side. So 841, 8421. This is the weight assigned to bits whenever we are going from lower to higher bit, and that is why sometimes we tell, okay, I want to write 5. How can we write 5? 8 1 will be 0. This will be 1. This will be 0. This will be 1. So what we used to do basically, we multiply the coefficients with this weight value, and in this way you write the number. We know this thing from decimal number system, we already know. So here, since we are representing your binary number with the help of 0 and 1, so it becomes very easy to represent, to write any number. Suppose I want to write here 15. So how can we write 8 plus 4? 12. 12 plus 2 will be 14 plus 1, 5. It means if all is 1, 1, then it becomes 15. Is it okay? I want to write only 8. So 8 position will be 1 and rest will be 0. Okay. So this is the weight binary based on the weight, and these numbers are in ascending order, means first number 0 0 0, then so on. It follows this pattern. Okay. But code is something little bit different. It it is coded. It is a kind of coded or mapping information. Okay, for a particular set of numbers. So we are discussing about here binary coded decimal. So decimal, we know whose base is 10. Okay, whose base is 10. So here 10 to power 0, 10 to power 1, 10 to power 2, something like that. We go like this. So this is unit, 10th place, 100th place, and so on. This is how we write the number in decimal number system. So in decimal number system, base is 10, and these 10 symbols are represented by this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, nothing new. And the corresponding BCD, binary coded decimal digit. Now we want to represent only with 0 and 1, all these numbers. So 0 is equivalent to 0, 0, 0. Then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. But if we use these 4 bits, so 4-bit number in binary goes from 0, 0, 0 to 1, 1, 1, 1. And this 1, 1, 1 is nothing but 15. It means from 10 to 15 binary number are not uh, given in the BCD, and that is why it becomes a code, not a number. Okay. So it's very easy. Means even binary number and BCD number from 0 to 9 are same. That this is as straightforward. And rest, if we want to write C10, you have to go to here. What unit you have to increase, means from unit place to 10th place, and then again you repeat the same thing. 1 1 1 2 1 3, and at unit place what is this number? 0 1 2 3 4, and this is one is common. So if you want, suppose now you can tell BCD number goes from 0 to 9 only, but suppose I want to write 12. How to write this 12 into BCD number? It is straightforward. How? 2 is represented like this, 0 0 1 0, and 1 is represented like this. So you write 0 0 0 1. What does it mean? We express a decimal number into Decibel form. N-I-B-B-L-E. Decibel means group of 4. Like we tell byte. Byte is group of 8 bits. Similarly, Decibel is group of 4 bits. So with the help of group of 4 bits, we represent directly your decimal number into BCD number. Now you can see here. This is what I am trying to tell. I want to write 185, 185. This is a decimal number system. That is why base 10. And this is the BCD representation. So you see 5. 5 is written as this. How can I say this is 5? Because I was telling here, no, this is 5. Because 4 and 1, so 0, 1, 0, 1. And this is what is written here, 0, 1, 0, 1. So this is your 5. And this group of 4 is what? Group of 4 is 8. and this group of 4 is 1 is 0 0 0 1. So 185. So easy. However, if you want to write this number into binary, that is really difficult. You have to go for successive subtraction method. And what is that? Okay, now turn has come. So let me take number, and then I will tell how to write. Suppose I want to write 6, because I cannot take so big number. I want to write 6 into binary number. So what I will do? I will do divide this 6 by 2. So 2 3 is 6. So 0 remainder, and this is what is called quotient. क्या बोलते हैं इसको? I forgot. Then 2 2 2 1 2, and remainder is 1. So 1 1 0. We have to read like this. So 1 1 0 is nothing but 6 in decimal. Is it okay? And how can we prove? You go here. This is 8 4 2 1. So this will be cross. 2 is there, 4 is there. The 4 plus 2 will be 6. 8 is not there. You can write 0 here. So this is 0. So 2 plus 4 is equal to 6. Are you getting? I think this you have studied in your previous classes, how to convert your decimal number into binary number. So similarly, this 185 is converted into binary number by successive uh, division. So 185 is like this. Now you see beauty of BCD. Beauty of BCD. This is also using binary number only. This representation or this symbol 0 and 1, but straightforward. So that is the advantage. And why we did basically BCD code? Because most of the time we deal with in our day-to-day life with decimal number system, that is 0 1 2 3 4. This we know, and in your laptop keyboard also these numbers are there. There is no such binary number, but your machine is working in the binary form. Okay, so straightforward conversion is possible in BCD, and this BCD is very important for representation also here. So you must have seen on your calculator, on your digital display. Suppose you go to railway station, so you might have seen these kind of symbols. These are nothing but 7 segment LEDs. 7 segment LED, light emitting diode. So this 7 segment, so A, B, C, D, E, F, G. How many are there? 1, 2, 3, 4, 5, 6, 7. So these are the 7, LEDs are there which glows. Okay. So if I want to represent 1, so this B and C LED will glow, rest LED will not glow. So we are able to see 1. I want to represent 8. So in case of 8, all LEDs will glow, all 7. So this will be A, this will be 1. I want to suppose display 0 to the user. So except G, all LED will glow. So to design such circuit, we need BCD to 7 segment decoder, because these numbers are basically BCD numbers, digital numbers BCD from 0 to 9. And then we have to represent BCD to 7 segment decoder. The popular name of this arrangement is called 7 segment decoder. So this is in your syllabus. In fact, chapter second unit, we will design this circuit. So BCD to 7 segment decoder. And this is the BCD representation. 4 bit is required to represent straightforward. Now here you can see 396. So this is 30011, and 9 we can write 1001, and 6 we can write 0110. Just I have converted your 6, so we can verify here. Okay, then moving to BCD addition. Yeah, in BCD addition, since we know our BCD number goes from 0 to 9. Okay. However, whenever we are going to do additions, it is quite possible that after addition, your number may be more than that. Suppose 8 and 9. 8 straightforward you can write 9 also, but after addition, this 17 is very difficult to difficult means we have to take another set of 4 bits to represent this one. So this then there is a need of correction. And what is that correction? You see 0 to 9 we can easily represent while adding, but from 10 to 15, how many numbers are there? 10, 11, 12, 13, 14, 15. There are 6. These 6 numbers are not uh, adjusted or not represented. So we have to add this 6 here. You see every time they add 6 whenever the sum is coming greater than 9. So here sum is coming greater than 9, so they have added 6. Here sum is coming greater than 9, they have added 6 to represent correctly BCD number. So it is an example here. What is that example? Basically number. Okay, so if we are writing here, say 4 plus 5, 4 BCD, this one, and we want to add 5. So since sum is coming 9, and we can correctly represent 9 in BCD form, so there is no issue of of representation. Okay, so that is why there is no need to add 6. However, if we want to write 4 plus 8, so it will be 12, and 12 is written as 1100, which is not a correct BCD representation. This is 1100 is not a BCD number. BCD number goes from 0 to 9 only, means 0000 to 1001. But here answer is 1100. So this is not a BCD number, but we want to correct it. So just add 6. How can we add 6? 6 is represented as 0110. This is 6. We add 6, and in this way this will be here number, and this one will be another set. So this becomes what? This is 2 and this is 1, and 1 2 is now correct representation of BCD. I hope I am able to make some sense. Okay, so this is the BCD, and then out carry, yeah, 6. Same example is given here. Then BCD code. Yeah,
Excuse me,
one
sir.
more. Yeah.
Sir, like in the previous case, you told us that if the if we have carry in the sign bits place, we discard that. So, sir, we will not apply that rule here.
No, no, this is BCD code. This is not a number. Those are the binary numbers complemented form. Negative numbers addition. BCD addition is different.
It means this that rule will not be applied here.
No.
Okay, sir.
Okay. 4 plus 5 added. 9 is coming. So 9 is correct form. It is valid BCD number. We call it is a valid BCD number. Here, suppose we want to add two numbers, that is 4 and 8. So what will be the answer? Normally in binary number this is 12, and it is very much as far as binary number is concerned like 1100. But this is not a correct representation of BCD. But there should be some mechanism. The mechanism is that we add 6. And why 6? Because these 6 were not defined. Okay, so we add 6 here in 12, and after addition you will get the answer in correct BCD representation. That is why I wrote here now 0010 is nothing but 2, because 4 bit. BCD is represented with the group of 4 bits, that is called nibble. So 4 bit we have taken, and equivalent binary number will be 2, and sorry, yeah, decimal number basically, and this is 1. You can put here 0, no problem. So this is 0001, so it will be 1 and 2, and 1, 2 is the answer, correct answer. Similarly, here also you can go. I want to add 8 and 9. So 8 and 9 is 17. 17 is written here in binary form, that is okay. But this is not a correct BCD representation. So in order to represent it correctly, we add 6. If we are adding 6, so you see group of 4 ones here. It is what? 0, 1, 1, 1 is nothing but 7. And this is 1 here, 0, 0, 0, 4 bit we want to write. So 0, 0, 0, 1. So it is 1. So this is normal case. Suppose a number is there. Left side, if you write any 0, it has no as such change in the magnitude. However, if you write this side, of course, magnitude is going to differ. Isn't it? Got it? Okay, now one more code in the same line I will cover. Where it is. Okay, this few codes are given here. BCD code, then access 3 code. These are two explicitly mentioned in our syllabus. That is why I will cover. And besides that, we have gray code also. I will cover in where whenever it turns come. So BCD number is corresponding to your decimal number is like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Decimal number. Its corresponding BCD number is same from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is represented as the way we write binary number. No issue because 8, 4, 2, 1. Same. Only issue is that whenever we want to write 10, so we have to separately write 0 and 0, 0, 0, 1. So this is a BCD representation of a 10 of decimal number. Now coming to this access 3. Access 3 as name suggests whatever number is there in binary, okay, whatever number is there in binary, we have to just start with 3. We have to add basically 3. So if we add 3 in the 0, we will get this 0, 0, 0, 1. That is nothing but 3. Then this 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is in the binary. However, this is equivalent of 9 in access 3 code. So philosophy wise, it is just adding 3 whatever binary number we have or BCD number we have. Okay.
Excuse me,
Okay.
sir.
Yeah.
Sir, what does that number 8421 means?
These are the weight, no? As I told you earlier. 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. So 2 power 0 means?
1.
Tell me. 1. 2 to power 1 means?
2.
2 to power 2 means?
4.
2 to power 3 means?
8.
Now you got it? 8, 4, 2, what?
Yes, sir.
Okay, good. So from there this came. However, still I want to point out BCD is only straightforward written from 0 to 9. Rest number, as I told you, what about others number? Suppose I want to represent 10. So 10 is represented like this. Okay. 20, say 13 I want to represent in BCD. So I have to write just 0, 0, 0, 1 and 3 separately. 0, 0, 1, 1. So that is the 13. Okay. And access 3 is we add 3. Whatever number equivalent number of binary is there or BCD is there. So next is gray code. Yeah, gray code is also one of the important code. It has a quality of, okay, where I should write. Yeah, here I can write. I will tell you the method. Uh, I will begin from very simple. This is 0, 0. We can write 0, 0. We can take from 2 bit only. The gray code says that there should be only 1 bit change Now it's adjacent. Whatever number you take, okay, there will be only one bit change. Suppose my pointer is here and I want to check here and here. Okay, so you see 0 1 0 0. This is your reference number. You go up, you go up, you see only one bit change you will observe. 0 is as it is, then 1 is as it is, 0 is as it is, 0 is converted now 1. So one bit change is, so by definition that is okay. Now come to down whether this definition is correct or not. So 0 is changed into 1. Okay, so one change is there. One is here, one is here, means no change. 0 is here, 0 is here, no change. 0 is here, 0 is here, no change. It means only one bit change is possible or allowed whenever we are going either up or down, or it says adjacent bit. Okay, got it? So this is the gray code. Now let us learn why it is called reflection code also. So this is 0 0. I want to write next number 0. Let us keep this as same, and 1. So what bit change? Now I want to write another number by keeping the same definition. So I keep this one as it is, then change this 0 to 1. Okay, then again I want to process, so I will keep this one as it is and change this one as a 0. So with the help of 2 bit we can write 0 0 0 1 1 0 1 1. This is the simple binary number. Okay, 0 0 0 1 1 0 1 1, and all these 4 combinations are already covered here. So this is your this is maintaining your gray code definition, means with respect adjacent bit should be changed by 1 bit. Okay, so decimal number equivalent, this is 0, this is 1, this is 2 in gray code, and this is 3 in gray code. Okay, got it? Till now any problem? And now you see by definition also adjacent bit is changed by only 1 bit. Now I want to write 3 bit. So you check here also 0 0 0 1 1 1 and 1 0. It is here 0 0 0 1 1 1 1 0. All are correct. Now I want to write 3 bit number. Okay, so what I will do, put a kind of mirror, put here 4 zeros and then similarly 4 ones, 1 2 3 4. Okay, and now since there is a mirror, so image of this 1 0 will be appear here, means nearer, so nearer, and farther the farthest. That is called reflection. So what is the first reflection here? 1 0. So I will write here, let me change the color, 1 0 here. Okay, same is coming, 1 0. Next is what? Next is 1 1. So I will write here 1 1. Next is 0 1. So I will write here 0 1. And next is 0 0. So I will write here 0 0. So you see, if I put here mirror, it is reflected here. And now see, now check which one. After 3 we have 4. So this is a 4. And how can we represent? With 3 bit only, 1 1 0. And here it is 1 1 0. Okay. Next is 5 triple 1, please. This is triple 1 1 1 1. And then 6 1 0 1 1 0 1, and 7 1 0 0. Okay, so I will write here 0 1 2 3 4 5 6 7. Got it? Now with the help of 3 bit, all numbers we have covered. With the help of 3 bits, number goes from 0 to 7, and this is what we have written, the all numbers from 0 to 7 is with the help of 3 bit all number have been covered. Now I want to write 4 bits. So put here mirror and write 8 times 0, 0, 0, 0, 0, 0, 0, 0, 0. 8 zeros, any problem? Then 8 ones, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and since this is a mirror, how should I put? Yeah. So reflection of this 1, 0, 0 will be here. 1, 0, 0. Then 1, 0, 1, 1, 0, 1. And after that 1, 1, 1, 1, 1, 1. Then after that 1 was 0, 1, 1, 0. Then 0, 1, 0, 0, 1, 0. Then 0, 1, 1, 0, 1, 1. Then 0, 0, 0, 0, 1, 0, 0, 1. And lastly is 0, 0, 0, 0, 0, 0. Okay. So you see this is 8, 9, 10, 11, 12, 13, 14, 15. So how to write gray codes from 0 to 15 is written here. And you can compare. Okay, last, oh, क्या हो गया? Sorry. I hope I'm able to make you understand how to what color. Okay. So you see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You check randomly. So whatever it is written here, same I also got. But what is that principle? Principle is reflection code as well as adjacent. Only one bit change with respect to adjacent. So last one is 1, 0, 0, 0. It is here. And I want to check this one. What it is? This is I think 8. And we are here 8. Got it? So gray code. How to write gray code from 0 to this? This we come to know here. Okay. So I think this ASCII code is not in your syllabus. So our book is with you. You can read. So with that, today's class is concluded. Any question is there? Please let me know.
So
So
do
can
we
we
need to
proceed
remember
to
all these codes?
Sorry.
So do we need to remember all these codes?
Oh, to avoid most of the mug-up things, I have given this logic now. You see the example gray code. Otherwise, I would have just read out and then telling that one bit change. Then what you would have done? You have remembered. But if you read the principle at 2 bit only, as far as this code is concerned, gray code is concerned. So you see it becomes very easy to write from 0 to 15. Okay. I will tell next in next class how to convert directly. Any code is given, suppose some binary number is given, how to convert, how to find out equivalent code, equivalent Greek code. Some binary number is there, how to convert it to its equivalent and vice versa. At certain extent, of course, certain extent, something you have to remember. Remembrance means it's principle we have to remember. No? And once we start writing and doing some exercise, it will be easy job. However, you see many things we just recall your decimal number system. Same principle is applicable here. In fact, many times like if we are doing addition or subtraction in 2's complement form, it is easier than with the decimal number system. Okay. So okay, then someone
excuse me, sir?
is coming. Yeah.
Sir, should we proceed the same procedure for the gray code, like every 1D for the number?